Yeah, so for those who haven't met me yet, my name is Dylan Nelson, and I'm excited to tell you a bit about some ongoing work we've been doing, looking at the the impact of a comprehensive feedback model on the process of gas accretion on the galaxies. And this is work in collaboration with many people, in particular Shai Ganel at Harvard and my thesis advisor, Lars Hörnquist. And our motivation here is really the big question of how do galaxies get their gas? In particular, what can the current generation of cosmological hydrodynamic simulations inform, how can they inform our theoretical picture of this process? And so to jump right in, I want to compare two simulations, one with feedback, one without feedback. And the no feedback case is a very simple run. It's a 20/8 megaparsec volume. It has the standard subgrid ISM pressurization scheme from Springel and Hörnquist, 2003. Stochastic Kennicutt-Schmidt-like star formation law with a very low density threshold and radiative cooling assuming a primordial gas composition, and no winds or outflows from stars or black holes. And this is a pretty standard run, 512 Q gas particles, same number of dark matter particles, giving a gravitational softening of about a kiloparsec, co-moving, and a baryon mass resolution of about 10 to the 6. And so to this, I want to compare the same or a different instance of the same initial conditions, but I want to add in the fiducial physics model from the illustrious simulation project with all the numerical parameters unchanged. And so when I'm forced to describe this, I sometimes call it a minimally comprehensive standard state-of-the-art, which is just a bunch of contradictions. By that, I mean that it's aimed to reproduce some key stellar observables, the redshift 0, stellar mass, halo mass relation, and the star formation rate density as a function of redshift. And it does this with models which have basically been developed and described in the literature over the past 10 years. And the list includes metal production and cooling contributions, black holes and black hole feedback from quasar and radio mode channels, and most importantly, for what I'll talk about today, our standard kinetic wind treatment. So in this model for stellar winds, so these generate galactic scale stellar outflows. And in this model, winds are generated directly from star-forming gas. And the wind velocity scales with the local dark matter dispersion, which correlates with the circular velocity maxima, and so the host halo mass. So the wind velocity goes up with halo mass. And the mass loading factor, there's the ratio of the wind m dot to the star formation rate, scales as 1 over the wind velocity squared, so it drops quite strongly with halo mass. And so to compare these two runs, I need a way to trace the evolution of accreting gas. And like any grid code, that's fundamentally impossible. You can't look at the Lagrangian history of any gas element because there's mass transfer between cells without reference to some sort of tracer particle scheme. So without going into any details, we've developed a newer, kind of a different scheme, which we call Monte Carlo tracer particles. And in the context of this more complicated physics, a nice feature of this is that it can self-consistently trace the flux of mass through all the baryonic components of the simulation. So for instance, tracer particles can move from gas cells into stars during star formation. They can return from stars back to gas cells as a result of stellar mass return. They can move from gas cells to black holes during accretion and between black holes during black hole mergers. So that's very nice consistency of how the mass fluxes can be followed. So using this scheme, the first thing I want to show you is the rates of accretion of gas onto galaxies. And there's some complications, unavoidable, which are detailed over here in this box on the left. And the first is the mode. So I don't care about merger contribution. I'm not interested in that. And I don't care about, that's clumpy. And I don't care about material which has been previously processed through a different system. That's what I call stripped. What I'm interested in is smooth, which is just my name for direct accretion from the IGM onto a galaxy. Another complication is that given the feedback, in particular the winds, we generate strong fountain-type motions in these systems, which means that the raw inflow rate into the galaxy in the feedback run will be very high. And to make a very a fair comparison between the runs, we're looking at the net rates, just the difference, the inflow minus the outflow into the galaxy. And finally, there's a question of origin, which is basically gas entering the galaxy. Is it coming into the main progenitor branch for the first time or not? So if it's coming in for the first time, I call that primordial. If it's coming into the galaxy, but it's previously already been in the main progenitor branch, I call that recycled. And so here, I'm comparing the accretion rates of smooth primordial gas onto galaxies, focused on massive halos around 10 to the 11.5. The feedback is in blue, and the no feedback is in green. And you see the general feature is that the introduction of feedback suppresses the rate of smooth primordial gas accretion at all redshifts, essentially. And I further segregate the accretion rates based on a look at the temperature history of the gas. So I compare the maximum pass temperature of each gas element to the halo virial temperature at the time of accretion. So the solid lines denote gas with a hot history, relatively hot. Dotted lines denote gas with a colder history. And perhaps what's most interesting here is that the ratio of the rates between the runs, the no feedback over the feedback, which is this inset here, which is a factor of a few up to maybe 10 by redshift 2, and it keeps going up towards redshift 0. This suppression ratio is independent of this temperature cut, which means essentially that the suppression of accretion by feedback doesn't care about the thermal history of the gas. It equally prevents accretion of either cold or hot material. So briefly, I want to look. What I've changed here is I've relaxed the constraint on the origin. Right? I want to look at all the accretion. I also want to include recycled. And no feedback lines don't change, which is good. The feedback lines get a boost at late times, right? As the recycled contribution contributes more and more to galaxies, such that the ratio actually hits unity around redshift 1 or so. And what's interesting is that these systems, we know that these systems of this halo mass have a pretty flat contribution to the star formation rate density at late times. And so this is implying that the recycled material provides a big support for star formation in these systems at late times, redshift less than 2 or something. So to provide a more qualitative picture of how what's the physical impact of the feedback, here I'm just comparing one halo at redshift 2, no feedback on the top and feedback on the bottom, showing the gas density projection, mass-weighted gas temperature, and mass-weighted radial velocity, where my convention is negative is inflow. So inflow is brown, outflow is blue and purple. So if you look at the temperature, you see that the introduction of intergenic feedback pushes out the hot halo gas to further radii. Also, our wind model generates extremely cold winds, which has an interesting effect of actually lowering the peak temperature of the hot halo gas in the inner halo. The impact on the inflow is most clearly seen here in the radial velocity. So at the virial radius, which is this circle, you see that a larger fraction of it is covered by outflowing material. And the consequence is a slight collimation of the inflow and also a slight reduction of the radial velocity. You could also say maybe a slight increase of the temperature, but it's minor. And the density, I would say there's nothing big going on at the virial radius. So let's be a bit more quantitative here. We can do that by looking at two instantaneous properties of the halo gas. And the first is just the spherical covering fraction of inflow or outflow. So by that, I just mean the fraction of the virial sphere or the quarter virial sphere, which is covered by gas with a positive or negative radial velocity. And so near the galaxy, at a quarter of the virial radius, we see that the feedback model suppresses the covering fraction of inflow significantly by about a factor of a half. And the consequence of that is that the fraction of that sphere, of that surface covered by outflow reaches about 50% at the maximum. At the virial radius, we see a slight increase in how much of the virial sphere is covered by outflowing material, but this signal kind of dies by redshift 0. And now if we look at the actual rates of accretion through these surfaces, we see that at the virial surface, the inflow rates are about the same across redshift. The outflow rates, we see a measurable but pretty small outflow of mass and metals out of the virial sphere in the feedback case. Now, closer to the galaxy, we see that the introduction of the feedback substantially increases both the inflow and the outflow rates through this surface, which is a kind of a clear signature of recycling proceeding through this radius.
What is outflow? How should I think of outflow in the feedback model?
All right, so outflow, I mean, there's kind of a residual, I think of it as kind of like a noise floor, which could be, I mean, it's mainly dynamical.
It's just orbits that are...
Right, it's an encounter and you have a tail that's going out. So there's outflow of gas. Yeah. Okay, so I focused mainly so far on smooth accretion from the IGM. I just want to comment really quickly, 2 minutes, on the relative contribution of the different modes. So smooth, clumpy, and stripped. I'm just showing here the fractional contribution of each mode to the total primordial accretion rate. And the most interesting thing here by far is in the smooth case that the feedback, which is blue, reduces the importance of smooth accretion by a few tens of percents, independent of redshift, for relatively hot material, same definition. And for cold material, it significantly suppresses it down towards 0 at redshift 0. So why is that? I'm plotting here just a histogram, essentially, of something that could be called the halo traversal time. This is just the time it takes gas to pass from its first virial crossing to its first incorporation in the galaxy. This is a histogram over all halo masses. And you see the effect of introducing the feedback as it shifts this to higher values by a factor of a few, 2 or 3, essentially saying that when you have feedback present, gas takes longer to traverse through the halo. Now, if we split this up by halo mass, we see 2 things. First, this shift is pretty much independent of halo mass, but more interestingly, the actual distributions of this time to cross the halo is also relatively independent of halo mass. And to tell you why this is interesting, I want to look at one more thing really quick. This is the fraction of gas in halos whose cooling time is shorter than its dynamical time. So in the simulation, this is the black line from the simulation. This drops at very low halo masses, and it's relatively constant from about 10 to the 10 to 10 to the 12. And these colored lines are very simple theoretical models given different density profiles. And this is interesting because in semi-analytic models of galaxy formation, they typically assume that this gas in particular, with short cooling times, is exactly that gas which is eligible to cool from the hot halo onto the galaxy. And they furthermore assume that there's some critical halo transition mass, which is indicative of these sharp drops, below which you have a rapid mode of cooling, so you have very short cooling time scales for all the gas, and above which you have a slow mode of cooling, so essentially none of the gas can cool. But what we find in the simulation, which is similar to this halo traversal time, is a very flat relation with halo mass, essentially implying that we don't see a strong evidence for any halo transition point above which and below which the process of gas accretion is strikingly different in the range of 10 to 10, 10 to 12, which is where you would expect it. So I'll skip this advertisement and jump to the conclusions, I think. So I've shown that the rate of smooth primordial gas accretion is suppressed by the introduction of the illustrious feedback model for massive halos. The spherical covering fraction of inflowing gas near the galaxy decreases, though the rates of both inflow and outflow increase substantially. This is a sign of the recycling. The fractional contribution of smooth accretion is lower, particularly so for material with a cold temperature history at redshift 0, which is almost entirely suppressed. And the halo transit time, or the halo traversal time for smoothly accreting gas, increases when you have the feedback, but neither it nor the fraction of gas with short cooling times vary strongly with halo mass. And this implies, again, that we don't see strong evidence for a critical halo mass in this range, at least in these 2 quantities that I've measured. Thank you.
We're running a little short. Maybe I'll ask Chung Pei to come and plug in. Do we have time for one quick question? Julie?
Yeah, how do you define smooth region?
Yeah, so I skipped the technical approach to that. The mode, which is smooth or substructure or stripped, et cetera, is defined at the time when the material is crossing the virial radius of its future host halo. So smooth is, the definition of smooth is that when it crosses the virial radius, it's not bound to any resolved substructure, and at all previous time, it has not been bound to any resolved substructure. Clumpy is obviously it is bound when it crosses, and stripped, it's not bound when it crosses, but at some previous time, it was bound to some other substructure.
Okay, well, thanks very much.
Thank you.